as a galvanic cell discharges, the reactants are being consumed to produce products. And therefore these concentrations are constantly changing. And the actual cell potential, the electromotive force, actually decreases. Once it reaches a state of equilibrium, when the cell potential is zero, the cell is said to be dead, and the concentration of reactants and products no longer changes because it's at equilibrium. We can determine the charge or the cell potential, the cell voltage, if we know the concentration of the reactants and products. And we can do this using an equation called the Nernst equation. And it looks a lot more scary than it actually is. There's only a few things that need to be identified in here. First off, R is a new value. We already know what cell potential is. T, I hope you all realize, is temperature, but when it's capitalized, it's usually Kelvin. So this is going to be our temperature in Kelvin. N and F are from the previous video. N is the number of electrons transferred in the reaction. F is Faraday's constant. Let's talk about R. R is a constant value, but don't worry, you don't need to memorize it. It's on your givens sheet. Just below Faraday's constant, it's right here. It's 8.3 volt coulombs per mole Kelvin. And the only other value here is Q. And Q is the mass action expression for the reaction. What the what? A mass action expression. A mass action expression is a ratio of the products to the reactants, and it can be calculated by setting up products divided by reactants. So in a reaction, anywhere where you see a multiplication sign, we're going to put anywhere you see a plus sign, we're going to multiply. Any coefficients are going to become exponents, and we're going to use brackets to symbolize the concentration of whatever it is we're talking about. So for example, with carbon dioxide decomposing into carbon monoxide and oxygen gas, these are the products, these are the reactants. So our first product is carbon monoxide, and since it has a coefficient of 2, that 2 becomes an exponent. We have a plus sign, so that becomes a multiplication. The concentration of oxygen gas, coefficient's 1, so we don't necessarily need to raise it to any exponent here, divided by our product, our reactants. Carbon dioxide is the reactant, so that's why it's down here. It has a coefficient of 2, so that's why our carbon dioxide is raised to 2. So if we were going to do decomposition of hydroiodic acid, see if you can do this. Hopefully you got an answer that looks something like this. So if we know the values or the concentrations of those reactants and products, we can actually assign a numerical value for Q, or for KEQ in this case. So let's do this problem. Write the mass action expression for carbon dioxide decomposing into carbon monoxide, and using these concentrations, determine the value for Q. First off, the mass action expression would be this. I'm sorry, it's a little cut off there at the bottom. And then we will just simply plug and chug in the values or the concentrations of each reactant and product. And our answer comes out to be 0.25. Now, you might notice that in all the previous examples, I've looked only at things that have the same phase, and they were stuck to mainly aqueous and gas. And this is because the concentration of a pure substance has a set density. And in solids and liquids, the density of a pure substance is not going to change. It's going to stay the same. And therefore, we're going to ignore it completely when you write out a mass action expression. So if iodine becomes iodine gas, the KQ would simply be the gas. So now that you've had that little flashback to Gen Chem, we can come back to the Nernst equation. But this equation is big, honking, and somewhat cumbersome. A lot of the um, a lot of the electrochemistry questions on the AP exam are going to stay to 25 degrees Celsius. If you see 25 degrees Celsius, you can do a big jump in the air. Please don't actually do a jump in the air, and be happy because you can actually abridge this formula because T is always going to be 298. So we can actually come out with what would be a shorter formula, and it would look something like this. RT and divided by 2.303 times R times T divided by Faraday's constant comes out to be 0.0592 volts. And if you divide that by the number of electrons transferred times the log of the concentrate of the equilibrium constant, or what we just calculated as Q, and subtract from the standard cell potential, so the cell potential at standard conditions, you can figure out the charge of any battery given the concentrations. So let's say we're asked to calculate the EMF at 298 Kelvin generated by a cell which uses the reaction below, and when these concentrations are at these set values. Well, first off, we can jump up in the air. Yay! 298 Kelvin, that is a standard condition that we can use to use the abridged formula. So here's our abridged formula. Notice that I'm noting that this is at 298 Kelvin. That's why I can use this abridged formula. And once again, I'm just going to plug and chug as I've been doing before. So let's pick one of these values first. Let's solve for the standard cell potential first off. So that's the half cell reduction potential plus the oxidation potential, which is the opposite of the anode. So that's going to give us, let's break this in half. Dichromate is going to become chromium and water. It looks like that's one of our half reactions. And iodine is going to go from being iodine minus to iodine elemental, so that's going to be oxidized. So if I look those up, I find that they have the following half reaction potential. Alright, so chromate, I think it's dichromate. I might be wrong. You'll correct me tomorrow. Is plus 1.33 volts. The reduction potential of iodine is a positive 0.54 volts, but since I'm taking the oxidation, I flip it, it's a negative 0.54 volts. Add these two together, and I've got my cell potential, which I come out to find is a positive 0.79 volts. So I'm going to plug that in right here. One variable down, 2 to go. Find out what N is. Well, I've already got this here, so I can look at this really quick. How many electrons are being transferred? Look at that. 6 electrons being transferred. So I can also sub in M from doing this. It's like a bargain bin of variables. I'm getting 2 for the price of 1. Alright. Now, all I got left is Q. So let me get rid of some of this stuff. And remember, Q is a ratio of products to reactants. So the only product here that is not a solid or a liquid is the chromium ion. So I'm going to make that my denominator or numerator. That's why I don't teach math. And on the other side of the equation, as our reactants, well, we've got everything. Oh, and again, this chromium ion is raised to the second power because that's the coefficient. So now all of this, we're going to have this as 1 This is another, that's another. We're going to have 3 things down here. Let's plug those in. Alright, this is an oxidation state, not an exponent, because because the coefficient out here is 1, so that's why it's raised to the 1 here. In front of hydrogen, there's 12. So 12 is our exponent. And in front of iodine, there's 6, so 6 becomes the exponent here. Alright, so now we just got to do some plug and chug. Concentration of the chromium ion is 1 times 10 to the negative 5th, so we plug that in. The dichromium ion's concentration is 2, so we're going to plug that in there. Hydrogen is 1 molar and iodine is 1 molar, so let's put those in. And our mass action expression, or our Q, is going to look like this. So now, all we've got to do is plug this into our calculator. And if I do 1.5 e negative 5 squared, I end up getting 1 times 10 to the negative 10th. 2 times 1 to the 12th, well that's just 1. 1 to the 6th, that's just 1. 2 times 1 times 1 is 2. So then, just divide. Our Q is going to equal out 5 times 10 to the 5 times 10 to the negative 11. Plug that value in for Q, and our equation is going to look like that right there. And now all we've got to do is solve. Log of 5 times 10 to the negative 11 is 10.30. Multiply that by this right here, and we end up with a negative 0.10 volts. Take that, add it to this, and we have our new voltage of 0.89 volts. Now some batteries don't work like I've been showing you so far. Some batteries work on a difference of concentration rather than a difference of species. So if you have the same species, you can have the battery work, it just has to have a different concentration. Even though the standard, the cell potential would equal 0 because you'd have the same thing on both sides, it works under non-standard conditions and will continue to do so until the concentrations equal out. And no matter what, the oxidation, so the anode is always wherever the most dilute solution is, and the cathode is wherever the more concentrated solution is. So that's where reduction is occurring. You can figure out the equilibrium constant for this reaction if you manipulate the Nernst equation, so that the log of the mass action expression, log of Q, equals the number of electrons transferred times the cell potential divided by 0.592. And that's only at 25 degrees Celsius. And I'm running out of time, so I'm going to have to run through this last one. So if we were asked to calculate the KEQ, or equilibrium constant, for the oxidation of iron by oxygen in an acidic solution, it would look like this. This would be our redox reaction. After we find out what the cell potential is for each one, we could figure out the cell potential for the overall reaction. And we would know that 4 electrons are transferred. Given that value, we could figure out what the mass action expression would be, or Q, for this, using the equation above, or using actually this equation here. And we would find that if you divided these out, you would end up with a K value of 1 times 10, or sorry, a Q value of 1 times 10 to the 31st. The Nernst equation, and its abbreviated brother. Know them. Love them.